Hi everyone, I'm Dan Greshkin. Welcome to the Biodesign Challenges webinar series. This session is called Biodesign in the Era of Automation. I'm very excited to have Zach Serber with us from Zymergen. And of course, we're really glad that you can make it today as well. Dan Greshkin, Executive Director of BDC.
And I'm Vina, I'm the Program Manager of BDC.
So I've said this before, but I'll say it again. The webinar series was created as a resource for participating students and instructors to share knowledge around the emerging field of biodesign. This year, we've opened our sessions that were originally for students and instructors only. We've opened it to the general public. So today's session features Zymergen, a company that designs microbes. Thank you, Zymergen. Thank you, Zach, for joining us in this year's Biodesign Challenge. And of course, thank you for being a sponsor this year as well. It's much appreciated by both us and the students. A couple of announcements?
Yes, and a quick announcement before we begin. We also have another webinar next Tuesday featuring Claire Bergkamp, who's the Director of Sustainability and Innovation at Stella McCartney. So we have more information on our Twitter that we'll be sharing at Biodesign as well. So be sure to check our Twitter page out as well.
So before Zach begins, I'll give you a little introduction on how we'll be running this webinar. You'll see in front of you that there's a chat bar. Ask your questions in the chat bar. You can ask them anytime. We'll be recording them. And then Zach will give a talk for about 45 minutes and go through his slides. And then we'll have a conversation using the chat as our forum for the questions and answers. Both Vina and I will MC that chat, so should go pretty smoothly. We're very excited about it. And we'll do our best to answer whatever questions you have after Zach's talk.
And lastly, I'd like to introduce you all to our speaker for today, Zach Serber. Zach is the Chief Science Officer at Zymergen and is responsible for their overall scientific direction. Prior to his work at Zymergen, he was the Director of Biology at Amyris and served as Principal Investigator on a DARPA contract to develop advanced tools for synthetic biology. Zach has 17 peer-reviewed publications in journals including Cell, Science, and the Journal of the American Chemical Society. He has 4 issued patents and has worked as a research fellow at Stanford University Medical School. Zach has a PhD in biophysics from UCSF, a master's in neuroscience from the University of Edinburgh, and a BA from Columbia University. Again, thank you, Zach, for joining us, and we will now turn our mic off so you can start speaking.
Thanks, Zach.
Terrific. Thank you so much for that nice introduction, and it's a real pleasure to be here today to talk to you all about design principles as they're applied to biology. My hope is to be responsive to your questions, so if things come up during the course of my presentation, please type them and I'll do my best to answer them in the flow. This presentation I've created principally for this audience because this venue forced me to think a little bit more deeply about how we explicitly apply design to what we do at Zymergen. And I'm going to begin by telling you a little introduction to how the company thinks about design in its pursuit of relevance and impact in the world. And then I'm going to talk about design as applied to 2 parts of what we do. First, I'm going to talk about molecular design, the choice of molecules that one can make from biology. And then second, I will talk about microbial design, how to optimize microbes for the purposes of making the products discussed in the first section. So as a way of introduction, I wanted to talk about oil. So a barrel of oil, about 85% of it is used for energy, mostly transportation, and it represents about a $3 trillion market. This is the crux of a big part of our current lifestyle and economy, and it is a very dirty industry, one that a lot of people would like to displace, and 15 or so years ago, people sought to disrupt this, and a bunch of startups were built around the idea of creating sustainable alternatives, particularly to transportation fuels. Unfortunately, that largely hasn't come to pass. The electrification of the transportation grid seems like a more plausible alternative to petroleum fuel than did once upon a time bio-sourced alternatives. And you see here in this bar chart some 5 companies all devoted to transportation fuels that went public. And what the stack represents is the value of those companies in aggregate. 2011 was probably the pinnacle of enthusiasm for this in the public markets, and the total value of the companies reached about 5.7 billion. And by 2017, it was about 400 million, a big decrease, representing several factors, not the least of which was the decline in oil prices. So when a barrel of oil is less than $100, it's very, very difficult for bio-based alternatives to be truly competitive. But there are other opportunities. So what is the other 15% of a barrel of oil used for? It's chiefly used for chemicals and materials. And despite being a much smaller volume, it's a much higher value. That 15% also represents about a $3 trillion market. And it wasn't always this way. So if one thinks about the world of 100 years ago, there were no petrochemicals. So 100 years ago, and this is a plot of materials versus time, 100 years ago, people relied on bio-based materials, including wood, bone, rubber, horn, things that came from the natural world. And in fact, it's not much appreciated, but the natural world was straining under the demands placed upon them by human civilization. Many species nearly went extinct in the quest for those materials. It's slightly amazing to me that elephants are still alive because their ivory was so prized for its wonderful material properties and they were actively being hunted. Same goes for whales being used for home lighting. It was actually the advent of an alternative source of materials that spared a lot of animals from extinction, and that was petroleum-based products. What you see in the purple ovals are a number of different polymers that were invented and reached market over the last century. And these are things we're very familiar with: polyester, polyvinyl carbonate, which is PVC pipes, ABS, etc. All of these materials came to pretty dramatically replace most of what we were already getting, or what we were previously getting from the natural world. And what the chart shows on the bottom right is a new resurgence of bio-based materials, but instead of being the sort of raw materials that one gets from nature in the form of wood or bone or horn, it is polymers made from biochemicals, things like polylactic acid, PLA, which was invented roughly 20 years ago, used in 3D printing predominantly, and in certain other plastic applications. So this is a picture of how our sourcing of materials has changed by the decade, and an explanation for how petroleum came to be such a predominant source. It is also true that each of those chemicals and materials made from petroleum began with crude oil that is broken down into substituent molecules and then are reconstituted into these elaborate chemicals. A lot of our modern world is actually based on molecular innovation. The use of particular chemical structures, either alone or in polymers, to make a variety of products. It also is true that applications such as human health and agriculture are heavily dependent upon the molecules used, either as drugs or as crop protecting agents. The use of molecules is widespread, and using petroleum as the chief source of those molecules has its limits. So I think we can appreciate that biology is a wonderful source of molecular diversity if only we could tap into it. There are millions of different species of microbes and other organisms on the planet, each of which contains thousands or tens of thousands of genes. And by using those genes in combination, you can produce near infinite number of novel molecules, many of which are in nature today, and some of which can be made through creating chimeric versions of biosynthetic pathways, drawing genes from different organisms. It is also true that a substantial proportion of the economy, around $250 billion worth of products, are currently made with microbes in fermentation. So the foundations for tapping into the molecular diversity available in nature are here. The manufacturing infrastructure and the know-how around manufacturing using microbes to express different chemicals exists. What has been difficult, however, is coaxing the microbes into making arbitrary novel molecules and then scaling it up reliably so as to be able to produce the novel chemicals at economically relevant amounts and costs. So this brings us to the most wordy slide I have in the deck, which is around Zymergen's vision. And our vision is to create a vibrant, sustainable future through biology. And these are my words as applied to our business. It is an attempt to encompass our motives and our philosophy. I think I start by acknowledging that we collectively, everyone on this webinar, I'm sure, wants to improve the world and humanity's place within that world. We all consume more than we give back by huge margins. It's even those of us who try to live sustainable lifestyles find it very difficult to not take more than we give. And the tendency to ask people to do without, to be more minimalistic, is, I think, practically unrealistic and also verges on neocolonialism in that many of the developing countries with populations who aspire to improve standards of living will depend upon many of the things that we in the first world take for granted. And we have to find ways of supplying all of humanity with the ingredients for happy, successful lives. We're also not the first to realize that biology may offer some better alternatives. We've already described how molecular diversity available from biology is vast, and it's possible to make one for one many of the same things that are currently derived from petroleum. And it's also usually true that biosourced stuff has a smaller environmental impact. It's not always true, by the way, but it is usually true. Unfortunately, and this speaks to the biofuels point, directly challenging established industries head-to-head with bioequivalence is a losing proposition. So one of my favorite examples is acrylic acid. Acrylic acid is used to make polyacrylic, and polyacrylic is a $10 billion market today, the majority of which is used as the absorbent beads in disposable baby diapers. And that is, so when you swaddle your child in a pamper, you are putting a petroleum absorbent around their butt. The interesting thing is biology also readily makes acrylic acid, and it is possible to go to biosourcing for that ingredient. And some companies tried to do it, but they couldn't reach a cost position that was nearly competitive with the petroleum incumbents, and they couldn't beat the market as it existed today. So which brings us to the fourth point. Instead, our tack at Zymergen is to introduce biosourced and superior products as a way of gaining traction and ultimately shifting the market to seeking bio-based solutions. We have at Zymergen built a platform to develop and commercialize bio-based products, and we've built a business around that to cultivate our platform, to gain market insights, and to improve existing bioprocesses. And I'll give an example of what I mean by superior products and the importance of that in a moment. Our molecular technology platform gives us access to new exciting molecules, and these molecules are relevant to many sectors through incorporation of new products, and the goal of them is to improve the quality of human life, provide superior solutions with less environmental impact, and ultimately come to replace petroleum. Someone wrote, is there a reason why petroleum became the source for many of these molecules materials mentioned earlier? Yes, there definitely is. The sourcing of the bio-based, for example, ivory and whale blubber, all of these things, because of their increasing scarcity, became more expensive, and petroleum, which was originally pulled out of the ground for making kerosene as a home lighting alternative to whale oil, people were looking for other ways to apply that crude in other applications. And companies like DuPont and Dow grew up around the revolution in petroleum chemistries as people looked for ways to take the chemical ingredients based in oil and make something of higher value from them. So I want to give a quick example of how what a difference it makes to pursue not just sustainability but superiority. So please text me if anyone on this webinar is using a cathode ray tube, which is the kind of old-fashioned tube televisions or monitors that were popular or exclusively available 25 years ago. I suspect no one is. Everyone's using some kind of flat screen monitor, whether on their laptop or even on their desktop. And those flat screens employ either LCD or LED technologies, and they grew in market proportion in no way because of their environmental impact. People bought them because they were superior monitors. They took up less footprint on your desk. They were more elegant. They were tended to be crisper. They also turned out to have a much lower environmental impact. So this bar chart shows the climate change potential in kilograms of carbon dioxide equivalents for, in blue, the manufacturing of the different kinds of monitors, in red, the use based on the electricity consumption, and in green, the end-of-life disposal of those ingredients. And when you look at the cathode ray tube, you see that it is higher in all dimensions than flat screens. So people adopted flat screen technology because it was a nicer user experience, but it also had a reduced environmental impact. And by metaphor, what we're trying to do at Zymergen is come up with bio-based molecules which confer a benefit on the use and the application so that people want them because of their virtues. And it will also so happen that they have a superior environmental footprint because they're bio-based. I'm going to give you some examples of that in the next section. So I told you I was going to talk to you about design in 2 dimensions. The first is going to be around molecular design. How do we choose what molecule to pursue as a prospective new product based on biology? So as I mentioned before, the demand for molecular innovation exists across the economy in multiple sectors. It does certainly in agriculture and healthcare, but for the purposes of this webinar, I'm going to focus on one case study around materials. Materials are enablers of new properties of the products you buy. This is another depiction of basically the dearth of innovation in material science in the recent generation. So what we're plotting here is the invention of new petrochemical-based polymers by decade. And the circle size represents the size of the market they've come to occupy. And the date is obviously when they were invented. And you see that in the 30s, 40s, 50s, and 60s, there was a huge number of new polymers invented. But in my lifetime, at least, there really hasn't been new polymers much invented. And those that have been very specialized and low volume. PLA, which is in the 1990s, 2000 era, that is actually a polylactic acid. That's a biopolymer. All the rest to the left of it are petroleum-based polymers. This limitation, this lack of innovation is primarily due to the fact that there's only so much chemical diversity based in a barrel of oil. One can do a lot of things with fundamental chemistry around creating molecular diversity, but it comes at expense and difficulty. And for people to create consumer products, cost is an issue. You'll see in the 1970s, there were a handful of new polymers invented, and these are all very specialty polymers. PEEK, for example, is a thermal stable plastic, which is used in some components that are close to the combustion part of your engine because of its temperature resilience. But it's a very small use application, and it's a very complicated looking molecule, very expensive to make. So at a very high level, if we think of petroleum as providing simple Lego building blocks to make simple products, biology ought to offer us the capacity to create a much greater diversity of chemical building blocks, represented on the bottom left by more advanced Lego pieces, which allows you to make more complex, more intricate, more satisfying products, like the Lego Death Star there. We begin at Zymergen by providing to our partners and people seeking to solve problems with biology with what we call a bioreachables database. This is a collection of molecules numbering in the many of thousands that we ought to be able to make readily via biology. We haven't necessarily made them all, but based upon our in silico analysis of the genes available to us and the chemical reactions they perform, it is quite likely we should be able to make any one of the molecules on this list. This list of molecules becomes the ingredients, the color palette we take to partners when we're trying to solve their needs, their unmet market needs through new materials. These chemicals are distinct and notably different from many of the things that are readily available from petroleum in three technical ways. And I understand not everyone, well, I'll explain it as best I can, but if you have questions, please explain, or please pose those questions. So one component of what's available from biology are chemical moiety, excuse me, molecules with multiple chemical moieties capable of performing different kinds of reactions, as represented on the left there. Also, what's available is the use of heteroatoms. This is basically incorporating sulfur, chlorine, things that are not carbon, oxygen, or hydrogen. And then finally, chirality. And this is a particularly powerful in biology, the ability to, for a given carbon atom, be able to dictate the orientation of the four bonds so as to create chimerically distinct components rather than a mixture of two mirror images of a given molecule. And then we can, based upon this in silico analysis, begin with a precursor molecule and create a lot of biodiversity as represented by the picture on the bottom. Someone asks, are we working with public transit agencies? No, so I should be clear, we are not working on transportation fuels. It is our angle on this opportunity that one needs to find places for biology to participate where biology brings some advantage to the application other than sustainability. I'm all about sustainability, we're all about sustainability, but if you lead with that, if that becomes the motive for people to adopt your product, adoption is going to be slow, if at all. People tend, despite their best intentions and what they may tell pollsters, actually make their purchasing decisions chiefly based upon product quality and product cost. The use of sustainability as a criteria for purchasing is pretty low on people's list when you actually look at their buying behaviors. And someone asked, how do you balance pushing novel things as opposed to competing head-to-head with established petromolecules to accomplish certain objectives? No, so I'll answer that question in the coming slides with a case study. So one area of particular rapid adoption of novel materials is consumer electronics and electronics in general. So the cell phone you have in your pocket is enabled not only by the software that has been programmed for it, but also by an amazing collection of materials that have been brought together to create that miniaturized, very powerful device. Some of that includes inorganic chemistry, but a lot of it does involve organic chemistry. That is, chemistries that are available to us through biology. And when we looked at the market for consumer electronics and the materials being used, we found a lot of unmet need. There were things that people wanted to accomplish with their next generation version of their electronic devices that could not simply be accomplished with what existed today. And here's a list, I'm not going to bother reading through it, of some of the kinds of areas that were ripe for disruption and ripe for innovation. And it was difficult for the petroleum-based chemistries to be offering the innovations that the manufacturers demanded. So I'll do a deep dive on flexible films. Many of you, I'm sure, have seen that Samsung and others have recently launched flexible cell phones, flexible displays. These are phones that you can fold up and put in your pocket and unfold. Some of you may also know that Samsung, who made their announcement this year, a few months ago, was very late in actually delivering that product. They had been promising a flexible cell phone for years. And the reason why they were so delayed was they couldn't find the materials necessary to create the flexible display. They have a solution today, but if you go read the press about it, you'll find that there's a lot of detractors. People who say, well, yes, it is flexible, but there's a crease. It doesn't seem to have the transmission that you really want from a glass screen. It has many problems. It is adequate for market launch, but it is also very expensive and not really ideal in all the properties available through traditional petroleum chemistry. When you think about design, and I'm not an official designer, I employ design, and there's a formalism for thinking about this, which I'm sure people in the audience are better versed in than I am, but ultimately you're trying to create a product or an innovation that meets the customer user experience, and the flexible displays that exist today barely pass the bar. There's a lot of room for improvement. Things that you need to have a flexible display include glass-like hardness, extreme flexibility, certainly optical transparency. You also, if you really want to create a foldable phone rather than just a curved screen, you want a very small bend radius without leaving a crease. And you need to be able to bend it repeatedly without it eventually cracking or breaking. That's a very hard set of design criteria to meet. So this is, I think, probably one of the few data slides I have in this section, but this is what's called a spiderweb diagram of properties that you're trying to meet for product innovation. So what you see around the outside of this circle are a set of criteria that you want ideally to be ranked a 5. 5 is good, 0 is bad. So you need it to be transparent. You need it to have a low yellowness index, but a 5 is still good. 5 means low yellowness index. You need it to have high surface hardness, high tensile strength, low cost. You don't want it to have bend fatigue. What you then see in yellow and orange, this line tracing around the circle, is the score of 2 petrochemical participants in the flexible display markets. These are people using traditional oil and chemistry to create flexible displays. And in B and A, you see that they have something. They have a film that works, but it has not as much transparency as you'd like. It tends to be a little yellowish in color. Its surface hardness is not ideal, ranking only a 2 or a 3. In the dotted gray line is Zymergen's biofilm. We've created a film based on a molecule derived from biology that scores better on almost every category than what comes from petroleum naturally. And moreover, it's cheaper than what you can arrive at through petroleum chemistry. So it has superior user experience as well as being lower cost. This is the beginning of a wave of products that Zymergen is developing to satisfy consumer needs in various markets using the virtues of biochemistry as opposed to petroleum sourcing. And it is our firm conviction that through iterative examples like this, we are going to shift the suppliers, the manufacturers' mindset away from petroleum, which is where they just reflexively go for solutions, and turn increasingly to biology. And in doing so, we are going to create a more renewable, a more sustainable economy in the chemicals market. So someone asked, how are the materials evaluated on the 1 to 5 scale? Good question. Each of these has a set of assays that are distinct that give it a score, and those scores, which may be on an arbitrary scale, are then converted into a 5-point scale. So for example, for transparency, and I don't know the details, I'm not actually a material scientist, but I work with a lot of them. You take your material, your film, you shine light through it, and you have a detector on the other side to measure the transmission of photons through the film. And the more photons that get through at a broader set of wavelengths, the higher a score of transparency you're going to get. Similarly, for yellowness, you can measure the yellowish tinge in an empirical fashion using the right equipment. Okay, so choosing the molecule is critically important. I think the takeaway from that last section is that if you are to try to replace the incumbent sector, that is petroleum chemistry, by producing the identical molecule that they already make, it's going to be a very tough battle for you to gain market share, for you to have the impact you seek. It seems like it should be the right path because there's already a proven market for example, polyacrylic for baby diapers, but the past has proven that the incumbents, the petroleum industry, is well entrenched and very hard to dislodge unless you can provide a solution that actually is superior in some fashion. That's design as it comes to molecules and selecting molecules to have impact. The second way I'm going to talk about design is around the microbes that we use to actually make that molecule, described in the last slide as an ingredient for flexible displays. So when one is developing a new chemical that is made via biology, in fact, when one is developing almost anything that is intending to reach commercial scale, it follows a progression that usually falls along an S-curve, like this black line here, where on the x-axis is the amount of effort you put in, and on the y-axis is the performance of that new innovation. And we can divide this into three categories. There's the discovery phase, where you're identifying the new innovation, the new molecule in our case, and the microbe to make it. Then there's a commercialization phase, where you're optimizing that microbe and optimizing the manufacturing conditions to reduce the cost. Usually the prototype that you create in the discovery phase is fantastically expensive. There's this old adage in that the first dose of a revolutionary drug costs typically many hundreds of millions of dollars because of all the innovation required, but ultimately the cost comes down through commercialization activities to make the manufacturing much more efficient. And then finally, even once you've commercialized it, there's still virtue in lowering the cost on an ongoing basis. By lowering the cost, you improve not only the competitive advantage of the producer, but also the number and range of applications that solution can be applied to. Something which may be a specialty chemical and only applied in very narrow specialized circumstances can someday, if the cost comes down, be much wider use. A great example of this is Kevlar. So Kevlar was first invented in the 1950s. It's a petroleum polymer, and as you probably know, first used as a fiber in bulletproof equipment in the 1980s. However, today, Kevlar is actually found in lots of consumer goods because the cost has come down sufficiently that it need not only be used in very rarefied circumstances. So at Zymergen, we have built a platform to traverse this S-curve from start to finish much more efficiently with less risk than ever before. And that's absolutely critical to unlocking the potential of all these biosolutions. If you cannot climb this S-curve well, quickly, efficiently, and get there, all the innovation on the molecular side comes to naught if you can't actually mass produce it. So I mentioned before that our production environment is actually fermentation. We put a microbe that produces these chemicals into something that resembles what you might use for beer or wine fermentation, albeit a little bit more high tech than that. And the microbe gets mixed with food, which is typically some kind of sugar and sometimes some oxygen, and they spit out that chemical. The product discovery we've talked a bunch about. There's also the product optimization, and we use design on the DNA level to tackle this problem. And I'm going to go into some details around that. It's also worth noting that the microbe that you use in that fermentation process is not predetermined. You can use baker's yeast, you can use E. coli, you can use many different kinds of organisms, and it matters. The choice of the microbe used in these processes affects the feasibility of producing the molecule as well as the ultimate long-term economics. So it is critical that one have a platform that's capable of exploring multiple different kinds of microbes for the production. And what you see here is us exploring the suitability of 4 different microbes called host 1, 2, and 3, and 4 across the top versus 7 different products. And the more pink it is, the more of that product was produced in that host. And if you look at product 3, for example, if you were to choose which host to use, you'd probably choose host 3 and not host 2. Whereas host 2 might actually be superior for product 6 versus host 3. Also, that the choice of hosts not only affects the early production, but also the late stage optimization, because different hosts are going to be more resilient to large-scale fermentation of that given molecule than others. On this slide, and this is a bit technical, but we're comparing the suitability of 2 classes of microbes for producing over 100 different chemicals. So this is a more focused in terms of microbe level, but more broad in terms of the number of products. Prokaryotes basically means bacteria. Eukaryotes in this context mean yeast. And what we're looking at is the feasibility of using bacteria versus yeast to make a whole bunch of different kinds of products. Those in the green circle are products that could be readily made in either bacteria or in yeast. But then those in yellow are ones we tried to make in both bacteria and yeast, but were only successfully made in bacteria. And in blue are the ones only successfully made in yeast, not in bacteria. Right now, unfortunately, there's no way a priori of knowing for certain which microbial species is going to be best suited for producing a host, so you got to actually try it. Colin asks, does Zymergen intend to act as a supplier for these new biomolecules or as a material consultant for other companies? The answer is actually both. So we are supplying molecules to folks, and we are helping them solve their materials needs through consultation. So they will explain that they have some need in their application for chemical innovation, for molecular technology, and we will innovate solutions for them using our unique access to all those biomolecules I described in the bioreachables list. Someone also asked, how do you ensure constant yield and quality? Very good question and very important. Fundamentally, we employ best practices in manufacturing. So in much the same way that Anchor Steam Brewery or Sierra Nevada ensure consistent quality of their beer through process control of their fermentation, we can do the very same thing, except our microbes aren't making alcohol, they're making some other higher value chemical. And then Michelle asked, how did you choose the optical film molecule to pursue? Was there experimental data that showed that those molecules could be readily made and have superior qualities? So that's a key question, and it would take a long time to answer it in full, but in brief, the successful conversation, if you will, between the biologists and the chemists is key to arriving at a solution. The biologists know what molecules biology can make, and we have a list, a catalog, if you will, of thousands. And the chemists have an idea of what chemicals would actually satisfy their needs, many of which are not available from petroleum. And so you're basically in a Venn diagram looking for the intersection between need and availability. Daniel asked, do you use directed evolution in strain engineering? Yes, in a process I'm about to describe. The definition of directed evolution can vary, but you'll see what I mean in a second. So I think it's also worth noting, especially for the people less familiar, that design space in biology is absolutely enormous. If you think about every creature living on this planet today, and every creature that has ever lived on this planet or will ever live on this planet, those are all just variations on DNA design. Now, it's designed through evolution, but nonetheless, variations in those DNA sequences elicit everything as diverse as a woolly mammoth to an amoeba. The size of that complexity, of that available search space or design space, is held up against certain other seemingly very difficult problems. So I'm sure everyone on this webinar knows that artificial intelligence has been used to win at games like chess and Go, and the number of solutions to the problem of Go is 10 to the 360th, which is 1 with 360 zeros after it, a truly massive number. But if you just look at the number of variations of the human genome, it's 4 to the 3.2 billion zeros. And that, I can explain how those numbers are arrived at, but the point is it's just a massively larger number. Historically, we have tried to rely on human hypothesis and understanding to make progress in controlling biology for this kind of technology, and it is our considered observation that that's wildly inadequate. So the traditional method on the far left is a scientist would generate a hypothesis in their head based upon their understanding of the system, and then they would conduct the experiments manually to explore whether their hypothesis was correct. Let's say they are trying to make a molecule used in flexible displays. They are going to have some intuition based on their broad understanding of biochemistry how to do that, and they're going to then try to carry that out in the microbe. Truly, more often than not, that doesn't work. Sometimes it does, and the current advent of biosolutions is largely based upon the rare instances of success, but it is more failure than success. Then you can bring automation to bear. And the scientists continue to generate the hypotheses, but robots actually conduct the experiments. This has been increasingly true over the last decade and is a huge labor saver and also an ability to try many more things. But you're still limited by the limits of human understanding of the system. If your hypothesis is based upon your best understanding of the system, it's worth noting that biology is massively complex and we don't actually know all that much about it. And intuiting what to do next from a hypothesis generating point of view is very tough. So what Zymergen brings to bear is a combination of robotics to conduct the experiments and generate data, and also algorithms to get beyond the limits of human imagination. We treat the genome of these microbes used to produce these chemicals as a search space to optimize, much in the way that other algorithms traverse other design spaces. So I realize that this use of design may not be perfectly fungible with the way the audience often thinks about design, but it's certainly how we think about design a lot at Zymergen. The whole platform depends upon three pillars. We need to have cutting-edge molecular biology, the ability to modify the genome of these microbes with exquisite care and precision. We can do insertions, deletions, and substitutions of anywhere from a single base pair up to tens of thousands of base pairs in the genomes of these microbes using our platform. It's also very automated. If you were to visit our facility, you'd find literally hundreds of robots performing the liquid handling manipulations that are historically handled by people pipetting with their fingers. And then finally, and perhaps most importantly, is our computational power. We have a flexible data infrastructure that stores all the information collected through this exploration conducted by the robots. And we have a set of analytical tools that allow us to mine those data for opportunities and to figure out how to be more effective at design in the future. Let me get more specific. So this is a representation of our system. The left represents the traditional methods, the right represents the Zymergen method. The rectangle, the white rectangle, is intended to represent design space, or the genome of the microbe. And on the left, there's basically historically been two ways of altering the system to make it make what you want to make or make it more efficiently. And that's through human-directed engineering designs, basically human-based hypotheses, or randomness, random mutagenesis. So in the black diamonds, after someone has read all the literature and come to understand everything that is known about the microbe and the genes employed, one can actually do some targeted changes to try to affect it for the good. Usually some progress can be made that way, but not enough to achieve maximum optimal economics or performance. People then often resort to random mutagenesis, which means simply exposing the microbe to some mutagen, UV light, or a chemical carcinogen to introduce truly random changes, and you're then screened through all that diversity looking for that very rare instance in which the microbe has exhibited Wolverine-like properties rather than leukemia. Most often those changes are deleterious, but occasionally they're incredibly positive. On the right is a Zymergen approach where instead of applying human rational approaches or randomness, we actually grid up the genome and then systematically explore it with our search algorithms. This means no rock is left unturned. We try just about everything, and we get smarter by employing this approach over and over again as to coming to learn where the opportunities actually lie in a genome, even if we don't have the full mechanistic understanding of what's going on. Someone asks, will there be a human bias in the application of AI algorithms? For example, bias from data quality and quality? If so, how does Zymergen try to avoid such biases? There certainly is biases, and there are biases built into it also by the kinds of problems we're tackling. The algorithmic solutions we arrive at are generally focused on the narrow application of trying to improve the titer and yield and productivity of given molecules we're making for material science applications, and is not going to be generally widely applicable to things other than that. There's also the broad question is if you learn things based upon your work on bacteria, is it going to be useful in yeast as well? And we have some observations as to what extent that bias matters and doesn't matter. So we try to control for it, but in truth, we don't worry about it overly much because generally speaking, we can make progress. There's so much progress to be made. The bar is so low that even with those biases, one can still make spectacular progress. Sarah asks, Michelle asks, how much data is required to index that broken up genome? Michelle, could you ask that question a different way, perhaps? How much data? I don't quite understand the question. And Sarah asks, why are molecules made by both prokaryotes and eukaryotes produced in higher titers? In order to achieve higher titers, is our goal to optimize for both host types? Typically, we choose a host based upon the best long-term economics as well as the tractability of that host for producing that given molecule. So we tend to gravitate to one or the other, and even within bacteria and yeast, we tend to focus on certain particular species of bacteria and yeast as is well suited to the problem we're trying to solve. And why are they produced in high titers? Because we've asked them to. We've engineered the microbes to produce them in high titers. And typically the titers we begin with are not what we end with. It's all about climbing that S-curve. And do you think that high throughput data-driven bioengineering like Twist Biosciences will become the standard? So I'm going to unpack that a little bit. So Twist is a great company, and what they provide are the DNA ingredients for doing the work. So far as I know, and I'm pretty sure about this, they don't actually do any of this kind of data analysis as to what stretches of DNA that they're delivering are actually valuable. They are basically an ingredient provider, but they're not judging the ingredients. They fulfill orders. So companies like Twist ship plates full of DNA, but the sequences of the nucleic acids on that DNA are dictated by the person placing the order, by Zymergen, for example. So moving on, another place in which we apply machine learning is when we try to stack different genetic perturbations on top of each other. So we scan the genome looking for changes that confer a benefit to the microbe in producing the molecule, and often we find a lot. If we make 1,000 strains, for example, we might find 10 or 20 of those that we've engineered actually show some benefit. And that invites you, since you did them all one at a time, to start compiling them together. Compiling them together actually takes longer than you might think, and so we've built some machine learning algorithms to mine those data and to make predictions as to which pairs or triplets or quadruplets of discrete improvements are liable to be additive with one another. They aren't always. And in fact, if you truly and exhaustively explore all the combinations, it exceeds the throughput of our screening capacity. So it's a useful down selection that the machine learning provides. NA asks, how do you assemble your DNA constructs? Oh, a variety of methods. So I think people have become a bit obsessed with the assembly methods, and we're truly pretty well agnostic as to the assembly methods. I mean, there are a couple that we prefer, but we're not wed to any in particular. We employ a bunch of different kinds. Our company is quite young. We're only 6 years old, but over the course of our 6 years, I think we've used half a dozen different assembly methods, and we continue to use a couple to this day. Here is some concrete examples of us improving a microbe. So here we're looking at two key dimensions of performance of a microbe used in fermentation. On the y-axis is productivity. That is basically the speed with which the microbe spits out the molecule of interest. And across the x-axis is yield. This is the efficiency of conversion. How much food does the microbe need to consume to produce a given unit of product? And in general, you want to improve both of these dimensions. The importance of productivity versus yield is a function of the particular product and its application, but generally speaking, both matter. And there is a line drawn across this graph, which is basically a theoretical envelope of what's possible from a first principles point of view, from a physics point of view. How fast can it get, and how little food can you consume to produce a given amount of product? We began with a microbe that was about 50% of both of maximum, and through iterative designs and employing our platform, we have migrated the population both to the right and up, and we've produced a microbe that's almost at 100% of maximum productivity. And there's, by the way, a trade-off between the two. You can't get 100% of both simultaneously. And where you want to be on this curve is dependent upon the economics of production. But what you see is we began in blue, we've migrated more and more into the red, and this is through iterative designs and testing. To get from the blue to the far right has required roughly 15 iterations of that design cycle, whereby we tried things, we found success, and then we aggregated success upon success in an iterative fashion 15 times. And I should also note that of those 15 discrete genetic changes we introduced into that cell with maximum yield, for example, only 12 of them were in places that we would not have predicted. Only 3 of them were in locations that a scientist with a good understanding of molecular mechanism would have predicted, which shows the power of giving design over to algorithms to find solutions, particularly in very complicated design spaces like that of biology. So I see there are a couple more questions. I'll come to them in a moment. I'm almost at the end of the talk. I wanted to finish with a thought-provoking question, which is how will the advent of bio-based molecular technology change the world over the next 30 years? It's something I've given a lot of thought to. And if what we're doing at Zymergen catches on, if we have commercial success and others are inspired as well, the next wave of materials innovation is going to come from biology, not from traditional petroleum chemistries. What will that mean? Well, it will mean that though materials innovation has slowed, it will now accelerate. There will be a renaissance in molecular technologies. We'll find new materials with exciting properties, stronger, lighter, more thermal stable, more diverse materials to solve a wealth of different problems we have. Things we can't even imagine that a material can solve are reachable and solvable with the right kinds of materials. Also, those new materials are going to be from sustainable sources. They're going to be based on carbon not pulled out of the earth, but rather fixed out of the atmosphere, usually by plants or maybe even by the microbes themselves. They will be carbon neutral and chosen in part so as to have the minimum environmental impact. What will the follow-on effects of those kinds of innovations be? Well, it will improve the standard of living of people across the world. It will also change the economics of petroleum drilling in the first place. People drill oil out of the ground for the economic motives, and those economics are driven by both energy but also materials. And as we noted earlier on the talk, they are in about equal proportion. If we remove the financial incentive to mine oil for materials, it also changes the economics of energy, and it becomes less lucrative to drill oil for energy. This, in combination with electrification of the transportation grid and the use of renewable energies, are all going to form a suite of new technologies that are ultimately going to, from a market-driven way, reduce the dependence and need for petroleum, for digging fossil fuels out of the ground, for a variety of applications. And you need them together. You can't do it with piecemeal because our current economy is so based upon petroleum for so many different facets of our livelihood and our lived experience that you need to have solutions for all those facets in tandem from sustainable solutions to really wean the world off of oil. Okay, so that was my last slide of substance. This is the biofuture we look forward to, with large-scale manufacturing done in giant bioreactors, using renewable sources to create chemical diversity to solve the world's problems. And with that, I'll close and turn it over to the organizers to help synthesize the questions. Thank you.
Thanks, Zach. We appreciate that. I'm going to start with a simple question. You described 3 stages: the discovery, commercialization, and competitive advantage spheres in which one might prototype and then obviously advance a technology or molecule. Where does Zymergen actually sit in those 3 categories, or where does it like to sit in those 3 categories?
So we're today in all 3, but we didn't start out in all 3. So in as I mentioned before, we're a young company. We're 6 years old, but we are now over 700 people and still growing fast based upon our market traction. And our first market traction was actually in the competitive advantage segment of that S-curve. We began by working with people already employing biomanufacturing for producing product, and applied our algorithms and robotics to taking the microbe that they were using commercially already and enhancing the economics, basically reducing the costs of goods by improving the microbial catalysts that they were employing using our technology. And we found that we could make improvements above and beyond that which could be reached at by conventional approaches. And we chose that as our market entry because it was both a hard part of the S-curve. That final optimization is not much tackled and difficult. And also by working with people who already have product on the market and already manufacturing those products, we were finding a quick route to impact. One of the things for any young company, any entrepreneur, is you want to find a way for your ideas to reach market and have impact as quickly as possible. It takes a long time, even with our technology, to traverse that S-curve from start to finish. And if you want to prove to the market that you have relevance, if you want to generate revenue based upon success, we found that by serving the competitive advantage phase was the fastest route to that. But though we began there, we quickly started moving down the S-curve. We've also helped companies commercialize products that have been in their pipeline and have been difficult in climbing the steep part of the S-curve. And we, for ourselves, as well as for others, have innovated and discovered new molecules that satisfy unmet needs, more towards the beginning of the S-curve.
You described 300 different molecules that are possible according to your algorithm. That's a lot of molecules. How do you pick the ones you'll work on first? How do you prioritize?
Yeah, so it's actually a lot more than 300. In that figure, we began with 300 core metabolites, and then you can add enzymes on top of them to expand the chemical diversity you can reach. And we have in silico chemical pathways that go up to 27 steps away from core metabolism. And when you go through that many steps of enzymatic catalysis, you can reach tens of thousands, if not hundreds of thousands of unique molecules, simply relying upon enzymes that are well studied and understood today. The opportunity to grow that to even larger numbers is very much upon us by simply employing less studied, less well understood enzymes. But we don't need to. There's a lot of good that can be done by simply focusing on the few thousand that are closest at hand, those that are easiest to pursue. But you're right, how do you choose which of those several thousand to go make? There's no such thing as an intrinsically better molecule. It's all about what are the design criteria? What's it being applied to? So one of the things we've gotten quite good at Zymergen is trying to match this molecular technology we've got, all this catalog of molecules with application spaces. And so we choose molecules from our catalog based upon their ability to satisfy the need of some customer, or even more broadly of some unmet problem in the marketplace. For example, in electronics, we talked a lot about flexible displays. Another problem is that a smartphone employs over 70 different adhesives, 70 different glues in their manufacturing, because different substances, when you're trying to stick them together, require different chemical properties in the glue to actually adhere. We are working on more universal adhesives, things that will reduce the complexity of the glues that are used in manufacturing from 70 to just a handful because they are more universally applicable. That is a pretty narrow example of the kind of innovation we're finding, but it's a good one.
So you're getting a lot of questions from the audience around your business model. Who owns the products, or who owns the microbes that you make? What is, how do you divvy up how does your business model work? Why don't we address those, and then we'll go to some of the later questions.
Sure. So when we are working with someone who's already engaged in biomanufacturing, someone who is a mature player who knows what they're doing, and it's about improving their economics, as I described how we got our start in the market, what we do is we basically compensate it in two ways. We charge narrow fixed fees or modest fixed fees to sort of cover some of our costs as we do the work, but the majority of our compensation comes through sharing in the value we create. So when we deliver improved economics to our customer and they reap the benefits, we take a portion of that for some period of time. When we are innovating with a company who may actually have no exposure or familiarity with biomanufacturing or biosolutions at all, we have a different set of economic terms whereby we are bringing to them a molecular solution to their problem, as well as the unique sourcing of that through biology. And that is very much on a case-by-case basis as to how we collect or share in both the development costs as well as in the long-term positive economics. But in general, I would say philosophically, we put our money where our mouth is, we believe in our technology, and we try to set up contracts that align our incentives and reward us for impact.
All right, two more questions. We're after 2 o'clock, so I'll leave it with these two. And they're sort of in some senses, the opposite poles. One question is about, if the algorithms end up being so good, what role do synthetic biologists or people have in the innovation process? And then on the other end of the spectrum is we've already seen one bubble burst with biofuels. when do you expect there to be, well, how do I say it? Are we going to see another bubble and that will burst, or is there going to be a point where we really see this taking off?
Yeah. So the transition, so we're 6 years old. The algorithms we employ have not been employed through our entire history. We needed to accumulate the methodologies and the data to make use of them. And today, there's a mixture of algorithmic design and human designs in our work, depending upon the problem we're trying to solve. But the trend is definitely towards increasing amounts of algorithmic design. A lot of what we're doing algorithmically is to hardwire in our software or code into our software best practices and learnings from our data and from the synthetic biologists we employ. Moreover, people are finding it keeping plenty busy trying to optimize the operations of our systems, which includes the rule sets that we apply to problems to generate these kinds of solutions. So rather than trying to figure out as a synthetic biologist how to make molecule A, think about the design principles that you employ to make molecules A through Z and what the rule sets in the decision tree is around how you employ different tactics and design strategies against those different sets of targets, and then encode that into the platform. And the second question, I'm sorry, what was it? It was, are we in a bubble? Biofuels attracted billions of dollars of investment around the promise of displacing petroleum as a transportation fuel. And while the economics of that ultimately didn't work, and in part because of the collapse of oil prices, a lot of amazing technologies were developed with those billions. And companies like Zymergen and others are picking up the pieces of those technologies, of those broadly understood best practices, and combining them again around new business models. I genuinely think that, that the application of this technology to biofuels was not the best application. It had certain appeal for reasons I don't have time to go into, but the better application is for meeting unmet market needs, for finding applications in which the biology is not actually the leading remark you make, but we're solving your unmet market need. We're solving your problem with a molecular solution. The fact that comes from biology, as far as the customer of that, is an afterthought. It is an added benefit, perhaps, that it has a sustainable source, but it isn't the motive for the employing of it. Whereas with biofuels, ultimately, that really was the value proposition, that it was sustainable. And yes, there is a market for that, but it's pretty small relative to the size of the market overall.
Well, thank you, Zach. We're out of time. It's 2:04. We're a couple of minutes over time. Really fantastic talk. Really spectacular for our students and for instructors. This is a lot of food for thought for everyone involved in the Biodesign Challenge and, of course, the general public. Thank you, everyone, for joining us. Thank you so much, Zach, for doing this with us. I think this is going to be a benefit for us for really time to come. So thank you, everyone. We'll see you next week. Zach, thanks again.
Thank
we'll
you
talk
all.
to everyone
I'm
soon.
going to get to your question, but there are
it.
other ways to reach me if it's urgent. And thank you very much for providing me this platform and an opportunity to talk. Thanks so much.